My name is Sam Bentz, and for my Lab 9 project, I made a machine that turns sewing thread into yo-yo string. But what even is yo-yo string? A yo-yo string is a string like this. It's about 4 feet long, and then it's tied off on one end and cut to the player's preference, and this end simply attaches to the finger here, while the other end has the important role of attaching to the yo-yo. Where here you have this loop, and if I untwist it, I can then open it up like this and insert a yo-yo in it and twist it back up, and now the yo-yo is held secure. After a couple hours of use, the string often needs to be replaced as it loses its softness and gets thinner and dirty, thus necessitating the ability to either buy or make new strings. Making your own string has increased flexibility in terms of material, color, and thickness. Traditionally, to make a yo-yo string, you start with sewing thread and you wind it around 2 points about 10 to 12 feet apart, forming a series of loops. You do this usually around 6 times to achieve the desired thickness. Then, these loops are twisted together from one end with something like a drill. This twists the strands together into a string. This process must be done under tension, which is usually controlled by hand. If not enough tension is applied, the string will start to twist up on itself. As the string is twisted together, it contracts. Once the string has contracted about 10 to 15% of its original length, it is folded together and slowly relaxed by twisting it in the opposite direction. During this relaxation process, the strings twist together, forming the helical structure of the string. The string also regains some of its length. The improvements I set out to make when designing my machine was, number 1, to make it take up about half as much space by twisting the string together while it's already folded. Normally, due to the folding and shrinking of the string, you need about 12 feet of floor space to make a string, while my machine is only about 5 feet tall and takes up much less floor space as it stands vertically. Secondly, I wanted to implement consistent control of the tension and shrinkage throughout the process. This is where the use of sensing, logic, and actuation comes into play. My machine houses all of its electronics in the 3D printed base. In the front, there is a 9-volt power input, an Arduino Uno, and a brushed DC gear motor attached to a 3D printed gear train that is used to twist the thread into string. On the back, there is a dual H-bridge used to control the motors, along with a load cell with an amplifier circuit. Mounted to the load cell is a worm gear motor with a spool of fishing line attached to it. This worm gear motor also includes a magnetic encoder. The fishing line on the spool runs all the way up to the top of the machine where it goes around a pulley. This fishing line is used to apply tension to the hook on a linear rail. This hook is where the string is folded against. By mounting the spool motor onto a load cell, I can sense the tension that is applied to the string. The first step in using the machine is homing it. In processing, I will press the home button. This will cause the carriage to move down and then back up, and it will move up until it hits the end stop there, and the force will go up, causing it to stop and bring the carriage back down to a safe starting position. So after the machine is homed, I load it with this string. As you can see here, I have 6 loops loaded onto there. Didn't show it just for the sake of time. So now I will begin to set the parameters in processing. I'll set the target tension to 0.35 kilograms, and I'll set the shrink to 10%. I can save those, and then I can enable tension control. And as you'll see up here, it will then try to set the tension to the target tension using a PI controller. And sometimes it can't quite get there, so it will time out instead as it gets closer. So there, it's achieved pretty close to it. Now I will hit start twist, and down here, it will start twisting it together. And you'll see up here, it will move down to try to keep the tension constant, which you'll see in processing. So that worm gear motor will keep on releasing more line to try to keep the tension constant as the string is contracting, and the encoder will keep track of the rotary position, which gets mapped to a linear position until it reaches the desired shrink. So there you go, it stopped twisting. So for the final step, I've moved these hooks from the outer gears to the center gear. This way they twist together about the same axis, and this is where I will relieve the stress. So now I will hit start twist 2, and it will start twisting, and rather than getting shorter, this time it will get longer as it tries to keep the tension constant. So you see that happening. And once it reaches an inflection point where it stops from getting longer to start getting shorter because I've over twisted it, it will stop. And now if we look at the final result, we have a nice looking, very consistent and uniform yo-yo string that we can tie off at the end and put on yo-yo. Lastly, of course, we need a demo of the string. I'd say it works.